2, 1. In today's video, we're going to be going over sections 8.4. We're going to be looking at the alternating series test, absolute convergence, and the ratio test. So we're going to start off with the alternating series test, and the motivating example we're going to use is this one here on the screen. So it looks a lot like the harmonic, and since we know that the harmonic diverges, our question now is, does this diverge? And so this first term here might be a little weird, and so what you might want to do is just kind of investigate this by plugging in some numbers. So we have n, we have, all right, a sub n, and this is a sub n is in our entire sequence inside. Okay, so when I plug in 1, I'm going to get 1 over 1. That's not bad, we're used to that. But then when I plug in 1 here in the exponent, I'm going to get 1 minus 1 is 0. Negative 1 to the 0 is 1, so then this is just 1. Okay, so then I'll go 2. I'm going to get 1/2 just from the regular harmonic part, but then the negative 1 will make me negative 1 to the 2 minus 1, which will be negative. Okay, then I go to 3. I see that when I plug this in, I'm going to get a positive. And then 4, I'll end up with another negative, and so on. So then all of this negative 1 to the n minus 1 term is doing is it's alternating my sequence of terms between negative 1 and 1. So that piece alternates between negative 1 and 1, and then you just multiply that by, in this case, 1 over n. Okay, so you know, we're adding, we're subtracting, we're adding, we're subtracting, and the whole time our terms are getting smaller. So I was up here, and now I'm down here, and then up here, down here, and then so on. And my question is, okay, as I go out n to infinity, and I add up all those terms, what's going to happen? So, you know, again, starting off, this diverges, it's harmonic. And if I compare this to my actual series, well, when I add all these things up, it kind of looks to me like actually this is going to be bigger than our series we have here. Right? So if you just look at the terms, this first series would be 1 plus 1/2 plus 1/3 plus 1/4, and so on. But this series is 1, then you would add negative 1/2. So you just we'll just think of that subtraction. 1 minus 1/2 plus 1/3 minus 1/4, right? So that's bigger than this. And so this harmonic here was kind of right at the edge of, well, the terms go to 0, but it still diverges. So that was right on the edge of that happening. So we're getting something smaller, so, you know, maybe this converges. It's possible. Okay, so why don't we figure out a test to see if we can tell? So the test that we're going to need is called the alternating series test. And so if you have a series of the form negative 1 to the n minus 1 times b sub n, where b sub n is some other sequence that you're used to. In the example above, b sub n is 1 over n. So we'll just fix that for now. That'll be our b sub n. Well, there's two conditions here that we have to show. If our b sub n satisfies that the next term in the sequence is always smaller than or equal to the previous, so you can think of this almost like a function that's decreasing, and we can show that the limit of just the b sub n terms goes to 0, then the series is actually convergent. So let's think about ours. We got 1 over n. Is it true that 1 over n plus 1 is less than or equal to 1 over n? Well, this is kind of like what we were doing in the previous section when we were trying to show the convergence test. So we can cross multiply here. N is less than or equal to n plus 1. Okay, subtract n from both sides. 0 is less than or equal to 1. That's true, so this is true, so this is true. So it does work out. I have shown this is a true statement. Okay, so then our other one is, well, so I, this is the work for I. How about for the limit? So let's just do the limit. N goes to infinity of 1 over n. Well, we just know that's 0. You don't have to do any work there. As soon as you see that limit, you can say 0. Check. So what do we have here? We have our series, negative 1 to the n minus 1, 1 over n. We have identified out of the series a b sub n. We have taken that b sub n and shown the conditions I and II here. And thus, by the alternating series test, this series is convergent. That's it. I show condition, condition, I'm done. That's it. So this series actually is convergent, and it's convergent by the alternating series test. All right, so we got two conditions, we just have to show them. So let's try another example. Well, so we've got here negative 1 to the n minus 1. Or sorry, we've got negative 1 to the let me rewrite that. We got negative 1 to the n, 3 to the n over 4 to the n minus 1. Okay, so that's our series. So you might say, well, Gary, that's not in the right form. I need it to be alternating, right? I need to be to the n minus 1. Well, to the n or n minus 1, it's not going to be a big deal because we could rewrite this. And all we want to do is ask if it converges, right? We could rewrite this, take a negative out, then I am actually in the correct form. Oops, that's not to a power. So at this point, I am actually to the correct form. All I had to do is take one negative 1 out. So we're not going to really worry about that. If you see negative 1 to the n or negative 1 to the n minus 1, both are perfectly fine to use alternating series for. So our b sub n is equal to 3n over 4n minus 1. And our two conditions we need are, we need that it's decreasing, and we need that the limit of this goes to 0. So we need those conditions. So here's the thing. I'm looking at this, and I'm saying, well, I could start doing I, but something with number 2 doesn't look quite right to me. Because if I think about this limit, I actually know how to do this one. I make this 3x over 4x minus 1. At this point, I could use L'Hopital's rule, or we could use facts we know from previous courses where if I have a rational function, then I just compare the highest power, top and bottom. The highest pair top and bottom is 3x and 4x. Well, that's just 3/4, and that's the limit. So the limit of just the bn is 3/4. Does that fit my test? No, it does not. So in this case, the alternating series test does not apply. So that's okay. This didn't quite work out, but we have other ways we can try to attack this problem. And there's a couple different ways we could try to do this. So one way we could do it is to try to compare it to something that we know diverges. And I'm not saying necessarily that this has to diverge. I'm just saying that because the alternating series test did not show us convergence, it's making me think, and with this limit being 3/4, that yeah, maybe this isn't going to work out. So okay, let's check this out. So what I'm going to do is I'm going to say, okay, I think it diverges. So then I'm going to use the comparison test. All right, which means I need to put it above something else. And that something else I put it above has to diverge. Okay, so what I'm going to pick is I'm just going to take the fact that this -1 is bouncing me up and down and say that at the worst case scenario, it is -1, which means I can bound it here, right? Because at the smallest, this is going to be negative times 3n over 4n minus 1, or you can get -1 times that. Okay, so that's true, and that's not much to show. You just are using that fact that negative 1 to the n is between negative 1 and 1. Okay, and so then what we have to do is figure out what happens to this as a series, right? So we're interested in this series. Okay, so where I could just take the negative out because it's a constant. But you actually already did work for this. The limit of the terms of this new series I'm looking at as n goes to infinity, well, that's 3/4. So that's not 0. So it diverges by the test for divergence. Okay, so then we've got the comparison test. We've got a smaller series here that diverges, and that's going to push up our series and force it to diverge. So by the comparison test, our series diverges from n equals 1 to infinity, diverges. So just because you see a negative 1 does not mean you can automatically go and use the alternating series test. You have to be careful. You have to check all of the conditions. Okay. So here's another example. Again, I see alternating, right? And what I can do is I can take, to make this perfectly alternating, I can make that n minus 1 by pulling off 2 powers of negative 1. But when I do that, I end up getting negative 1 squared, negative 1 to the n minus 1, right? But negative 1 squared is just 1. So really I can just deal with it perfectly in an alternating form, where b sub n is n squared over n cubed plus 1. So what's number 1? I need that it's decreasing, right? So then I would need to show n plus 1 squared over n plus 1 cubed plus 1 is less than or equal to n squared over n cubed plus 1. Okay, so I would need to show this is true. And then in the second case, what do I need to do? I need to be able to show that the limit n squared over n cubed plus 1 as n goes to infinity, I want to show that 0. So this is what I need to show in order to use this test, the alternating series test. Okay, so this isn't the worst thing in the world. We'll start with number 2, because this limit isn't too bad. Remember, this is just a polynomial, so I'm going to switch to x's, and I'm going to use my rules from previously, where this limit is just compare the highest power on top and highest power on bottom, which is 1 over x. And as x goes to infinity, this goes to 0. So then this limit is 0. So again, we're just using the fact that higher power bottom is going to force you down to 0. Okay, so that one checks. Now, there's a couple ways to do this decreasing. You can either try to algebraically manipulate what we have written here, or you can switch this to x's, x squared over x cubed plus 1, and then you can take the derivative of this and just show that that derivative is negative for all the x's we care about. So we could try both of these. Let's start with the derivative way. So the derivative we're going to use quotient rule is, remember, low d high minus high d low over low squared. Okay, so what do we need to show here? Well, the bottom, because x is always positive, the bottom is going to be positive. So we need to show that the top is negative. That is, we need to show that this is always going to be less than 0 for all the x values we care about. Remember, that's x greater than or equal to 1 because that's what this says here. Okay, so let's play around. This is 2x to the 4th plus 2x minus 3x to the 4th would be less than 0. So this is what we're looking for. Okay, so then that's let's see here. So then this would be 2x minus x to the fourth is less than 0. Okay, so then I want to show that 2x is less than x to the fourth, right? This is what I need to be true for this to be decreasing and for this to be true. Okay, well, we know x is not 0, so I'm going to divide by both sides. Okay, and then since x is not 0, right, and x is also positive, so I don't have to flip, then I'm going to cube root. Okay, so then what we're seeing here when we do this is the cube root of 2 is somewhere between 1 and 2, a little bit bigger than 1, right? And so this is true as long as x is bigger than or equal to 2. So technically at this first step here, this is not necessarily true, but we're okay with that actually. As long as this is true eventually at some point and then going on this is true, we're going to be okay. So this is okay as long as it's true at some point and then forever, we're okay here. So if we have to go out to 2, that's not a big deal. So we've got our two conditions, and thus by the alternating series test, we converge. So you check the two conditions, you're good to go. You could, of course, have gone another way with this, where you're multiplying these n's everywhere, and you would have ended up with n cubed plus 1 times n plus 1 squared has to be less than or equal to n plus 1 cubed plus 1 times n squared. And so you're multiplying all those out, trying to move all the n's together to see what cancels, and trying to reason through that being true. So either way you want to go here is perfectly fine. Okay, so there is another way to do something like this, and it's called absolute convergence. So let's read that. It says a series is called absolutely convergent if the series of absolute values is convergent. Okay, so why would we use something like this? Well, there are instances where we'll have series that don't just look like all negatives, all positives, or alternating positive, negative. In this case that we have right here, we have negatives, but they're not just one negative, one positive, one negative, one positive, because cosine is positive sometimes, negative sometimes, and it's not every other term here. So what do we do here? We use this absolutely convergent idea, and what we do is we say, okay, I'm going to look at the absolute value of this over n squared. All right, well, that's just the absolute value of cosine n over n squared. Okay, and here's the idea behind this. So the absolute value of cosine n is always bounded. So this is bounded between 0 and 1. So this is going to be a useful thing for us. Okay, and so now we've got this sequence in here, this sequence right here, that is always positive, right? And so what we can do is use the comparison test. And the comparison test, the reason we have to do this is because that is only true for positive ANs and BNs, the two sequences that you have. So, but once we have this, we can do a comparison. Now to me, I look at this and I say, look, there's a 2 on the bottom. That kind of looks like a p-series, and 2 is bigger than 1, so convergence. So then what I'm going to do is say, okay, I think I can bound this by a p-series. And I indeed can, because look, I have cosine n, absolute value, the biggest it could ever get is 1, and so look, I put a 1 here as the top bound. And then these n squares, well, they match, so that's fine on the bottom. So this is true, and I know that this series converges because it is a p-series with p equal to 2, which is greater than 1. So what's the laundry list of these tests I just did? Well, I know that this converges. Why? Because, so I should say one more thing here. This converges absolutely. We're going to use the definition above, right? This converges absolutely because this series that I got by looking at the absolute value of my terms, right? So this new series that I got here, that converges because this converges. And why does this converge? Well, this converges by the comparison test. So I've shown that my series is absolutely convergent by using the comparison test on this new series that I got, where I just made everything positive. And there you go. Okay. So then the next one's a little bit of a doozy, but I don't actually think it's too bad once you get the hang of it. So the next one's called the ratio test. And so there's three options here. Option one is if I take the limit, where the limit that I'm taking is the next term divided by the previous term, right? If I do that limit, the absolute value, and I get a number, if that number is less than 1, my series is absolutely convergent, and therefore it converges. So this is really what you want to remember out of this, just converges. If I take the limit, and my limit is L is greater than 1, or infinity, then the series is divergent. If I take the limit, and I get 1, then the ratio test is inconclusive. And so it could be anything we don't know. All right. So, if you want to think a lot about what's happening here, what you should think of is you should look at this limit, and let's just make everything positive so I can drop the absolute values. Okay. So if this is equal to 1/2, just as an example, then what I am saying is when n gets really, really big, so when n gets big, then my sequence starts to look like an plus 1 is 1/2 a sub n. All I did was just multiply the a sub n on the other side, right? So then, and let me actually just change the notation here, because I'm not saying they're equal, I'm saying eventually it starts to look like it. Okay, so it's approximately that. All right, but we've seen this before, right? We've seen something where the next term in the sequence looks like a constant multiple of the previous. That is a geometric, right? So what I'm saying to you is, if I do this ratio test, I do this limit, and I get a number out with this limit, then I'm saying, my series, even if it's not geometric, it grows geometrically. In the long run, as n gets really big, it kind of starts to look like I'm just doing, in this case, half, 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 half. And what do we know from this? Well, if we're geometric, if our r is less than 1, I converge. If r is greater than 1, I diverge. So I'm just using this geometric idea that if I look at r, which is the number I'm multiplying each time, then what I can do is I can say, well, the ratio test is telling me my series, the terms in there, kind of look geometric eventually. So then I can use the ideas I know about geometric series and apply them to this this series I'm working with. And that's exactly what's happening here. This L less than 1, this L is like your R from the geometric. So if it's less than 1, converge, greater than 1, diverge. And what's nice about this, you don't have to even remember something new. You know this for geometric, now you know it for the ratio test. All right. Okay, so when do we use this? I think what you should think of is a couple things. First of all, this example I'm giving you right now, there's a mix of a lot of stuff. There's this term here that makes you think alternating, right? There's this term here with the n in the exponent that goes, oh, that's geometric. But then there's this other term here where you're going, oh, it's n to a power. That almost kind of looks like p series. So the ratio test is really good because it works for a lot of different series, even when the series looks like it's mixed up with multiple different ones. So right now, all we've been able to do are solve problems where the series look like geometric p-series, whatever, but they're off by just a little. This series, on the other hand, looks like it's got a bunch of things all mixed in together. So that's one reason that we might look for ratio. There's a second one, but I'll wait until we get to that point in doing the ratio test. So if I think maybe ratio works, I just have to immediately go limit. All right. Okay, so my a sub n is negative 1 to the n cubed over 3n. So remember, it's limit absolute value a sub n plus 1 over a sub n. So next term divided by the previous. All I have to do is just plug this into my a sub n. So this is limit as n goes to infinity. Absolute value, so on top I get plug in n plus 1 everywhere. Okay. And then on bottom, just plug in your regular old a sub n. Okay. So this looks like a mess, but if you are picking the ratio test correctly to use for these types of problems, it's actually going to be really nice. I'm dividing by a fraction, so I just flip the fraction. And you'll see what happens in just a second. So I flip the fraction. N plus 1 cubed over 3n plus 1. Okay, so when I flip this, I get this happening now. And don't forget your negative 1 to the n. Okay, and then I'm going to get cancellation. So here is where the ratio test is really nice. 3n and 3n plus 1 will cancel to leave just a 3 left over. Okay. N plus 1 cubed. It's not quite going to cancel with n cubed, but that's okay. We'll deal with that in a second. Negative 1 to the n plus 1 and negative 1 to the n. Those will cancel, leaving you just a negative 1. So let's rewrite that. I got the limit as n goes to infinity, okay, of negative 1 n plus 1 cubed over n cubed. Okie doke. And don't forget our 3. Whoops, don't forget your 3 there. Okay, so then we're taking the absolute value, so that gets rid of the negative 1. So that's really nice. N goes to infinity. And then every other term is positive, so I can just rewrite it like this. And we're almost done because I'm just left with a rational expression again, right? I've got n's to powers top and bottom. So what ends up happening here is you get the limit as n goes to infinity, right, of n cubed plus 3n squared plus 3n plus 1 all over 3n cubed. And then all we have to do is remember I can turn this into a Calc 1 limit by going to x's all over. And then I compare top to bottom, highest powers, which is 1/3. Okay, so I did my limit out. All right, I've used the ratio test. I did my limit. I go back. I say, okay, ratio test. My limit was 1/3. That's less than 1, so I am convergent. So L equals 1/3 less than 1, so convergent. So my initial series converges. That's it. You take the limit, you get a number, or infinity, or whatever. You go back, you look, see what happens. Okay, so let's try another one. And this one again is a little weird of one that I'm giving you here, but hopefully not too bad. So we've got here n to the n and n squared. So again, I'm looking at this and I'm saying, oh, I don't know what's going to happen, but I've got n factorial and then n's to powers. I might just be able to cancel stuff by doing the ratio test. So let's do the ratio test. A sub n is n to the n over n factorial. So this is the limit. So n goes to infinity, okay, of n plus 1 to the n plus 1 over n plus 1 factorial, okay, divided by n to the n over n factorial. So I'm going to flip, so that gives me n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. Okie doke. I'm going to get some cancellation here. So cancel, and this leaves n plus 1 on the bottom. All right. Okay, so then I get limit as n goes to infinity of, and everything's positive here, so I don't need the absolute values, so we can drop the absolute values, of n plus 1 to the n plus 1 over n plus 1 times n to the n. Okay, but on top, this is n plus 1, and I have n plus 1 copies, but I've got one on bottom too, so cancel, this goes to n. So this is limit n to infinity of n plus 1 raised to the n over n to the n. Okay, but I've got two different numbers raised to the same power, so that's limit as n goes to infinity, right, of n plus 1 over n to the n. Okay, so this is limit n goes to infinity of 1 plus 1 over n to the n, which is equal to e to the 1. Pausing for dramatic effect. So this is just a limit that maybe you've seen before in Calc 1, maybe not. It's an interesting one. I'm not going to hold you to being able to run through that whole thing on like a quiz or a test, but it is a pretty fun one to go through, and it's really interesting as well. But in any case, we get E, but that's approximately 2.71. So I go back to my ratio test and I say, okay, my L is bigger than 1, approximately 2.71. That's bigger than 1, so diverge. All done. So ratio test, get your limit, see what happens. Okay, so that was all we had for this. This is a pretty monstrous section, but the ratio test is going to be very important for us going forward. So we're going to really want to make sure we take the time to understand what's going on with this test. All right, thanks for watching, and I'll see you later.